the concept of oxidation number. Oxidation number of an element is defined as the electrical charge it appears to have as determined by a set of rules. And those rules are as follows. The oxidation number of every element in the uncombined form is 0, of which in chemistry we deal with element, atoms, and all the rest of them. Every element in the uncombined form has 0 oxidation state. Just like sodium is standing alone there, it's not combining with anything. So its oxidation number is 0. Every element, as much as elements they have 0 oxidation number in their uncombined state. Number 2, the oxidation number of a simple ion has the same size and the sign as the ion. As you can see from the example there, hydroxide ion, the oxidation number there is -1, chlorine is -1, calcium is +2, and so on and so forth. So that is it. Chlorine is -1. Just mind you, the oxidation number is always written on top, especially when the element is involved. But when you are writing them ordinarily, you now write them down. The algebraic sum of the oxidation number of every element in a compound is 0, and of which you know that a compound is formed when elements combine together. A compound is formed. So if you want to get the oxidation number of every element in a compound, it must be 0. I think we need to prove that. But before that, let's go to the rule number 4. In most compounds, the oxidation number of oxygen is -2, except in peroxide, where it is -1. Let us prove this number 4 now. The algebraic sum of the oxidation number of every element in the uncombined state is 0. Let us see how it goes. Okay, let us look at example 1 there. As you can see, calcium triisocarbonate 4. Let us prove that, the elements involved in calcium triisocarbonate 4 are calcium, carbon, and the oxygen. Calcium, carbon, and oxygen. That is the compound, that is the element that made up calcium triisocarbonate 4. And if you watch, the oxidation number of calcium is +2. The oxidation number of carbon is +4. And that of oxygen is -2. So we have 3 oxygen atoms. That was why I multiply -2 times 3. So when you now check +2 +4, and of which you know that minus will always cancel positive. So negative or positive is negative. So that is why it's -6. -2 times 3 is -6. So when you now check +2 +4 is +6. +6 minus 6 is 0. Is 0. So that is it. Now, if you watch from the other side, you see that sodium tetraozo sulfate 6. Sodium there, the oxidation state of sodium there is +1. Now, +1 times 2 plus sulfur is 6. Oxygen is always -2. Remember our last rule? So when you now do all these things, you get 0. The same thing with this one, HCl. Hydrogen is +1, and the chlorine is -1. +1 minus 1 is 0. So that is to prove that every compound, the algebraic sum of the oxidation number of every compound is 0. Any compound you can think of, once you add the respective oxidation number of every element there, it must give you 0. This concept of oxidation and reduction reaction, you need to get all these things in place before you can now go over to the broader one, that is balancing of redox equation. So I'm taking you through all these things so that when you now meet balancing of redox equation, you won't find it very, very difficult. So these are the rules for oxidation number of every element. But we are going to do a calculation because oxidation number is directly linked with the IUPAC name of a compound. Like if you had me very well in the first place, I was saying this one is a calcium triosocarbonate 4. Where did that 4 come from? This one is a sodium tetraososulfate 6. All these things I'm mentioning are the IUPAC names. How come about those numbers attached at the last of the name? So oxidation number plays a role in determining the IUPAC name of a compound. Let us check an example now how it goes. Let us check these examples on the board. Calculate or find the oxidation number of the underlying element and hence its IUPAC name. The first one is there. The underlying element there is C. B, the underlying element there is manganese. And C, the underlying element there is chromium. So let us see number one. The first rule, the first thing you should do is to equate the whole thing to zero. That is the first step to take. Check that A now. I'm going to equate the whole thing to zero. Remember that they asked us to find the oxidation number of the underlying element. The underlying element there is carbon. So we are going to find the oxidation number of that carbon. I have said the first rule or the first step to take there is to equate the whole compound to zero. So if you watch, I have equals everything to zero. Calcium there, the oxidation number is +2. Carbon is the one they asked us to find, plus oxygen. Oxygen. The oxidation number of oxygen is -2. So we have 3 oxygen atoms there. So that is why I multiply -2 times 3. If you check it very well, you see, check it very well now, you see that calcium +2, carbon, oxygen is -2 times 3, equal to 0. So if you just check it now, +2C, -2 times 3 is -6, equal to 0. Collect like terms. C come here, +2 minus 6, equal to 0. So +2 minus 6 is -4. And of which, when you collect like term, C will go one side now, the numbers will go one side. You now have C equal to +4, which means actually the oxidation number of carbon in this compound is +4. And that is why the name of this compound as a whole is calcium triosocarbonate 4. All these numbers at the end doesn't come by incidence. It comes about as a result of its oxidation number. I've always encouraged my students, in cases like this, try to find the oxidation number of the element closest to oxygen. That will give you the IUPAC name. And don't get it confused. This trioso means oxygen is 3. When we will go to this one that oxygen is 4, it will be tetraoso. And this one have to be heptaoso. So always find the oxidation number of the element closest to oxygen. That will give you the IUPAC name. So for this one, calcium triosocarbonate 4. That is the IUPAC name of this thing. And you have noticed today that this 4 doesn't come as a result of this thing. No. It came as a result of the oxidation number of carbon in that compound. Let's go to example B. Example B there is KMNO4. Check the example B, KMNO4, of which potassium there, the oxidation number of potassium there is +1. The oxidation number of manganese is the one they asked us to find. Remember, it is underlined. Now, oxygen has -2 oxidation states. -2 times 4, because oxygen is 4 there, equal to 0. Remember, equate the whole thing to 0. That is the first step. In as much as it's not an ion. If it's an ordinary compound, equate it to 0. So next time, if it is an ion, we are going to equate it to the charge of the ion. But all these ones are not ion. They are just compounds. So that is why we are equating them to 0. If you do the mathematics here, you know, collecting like terms, Mn +1 minus 8 will give you -7. And when this -7 is crossing over the sign of equality, it will change to +7. So oxidation state of manganese in this compound is +7. And that is why the IUPAC name of this compound is potassium tetraosomanganate 7. Potassium tetraozomanganate 7. Remember, manganese when it is standing alone, manganate when it's now combining with something else. Remember, all these things are not, these numbers are not just, don't just call them. It is determined by oxidation number. Let's now take the last one. Let's now take the last example and see how it goes.